Okay, hey guys, I was going to talk to you for a minute about this first page and then one problem on the second page of your notes because it's kind of cool. I never thought about this until I taught this either. Again, this curriculum has really made me a better mathematician to see relationships and stuff. This seems a little bit extra, but it's kind of cool to think about. Okay, basically, they're taking your regular numbers and they are comparing them with polynomials because a lot of what we do with polynomials should make number sense to you. So they're using whole numbers to help you understand that. So, like the number 132, they're saying, well, look, it's kind of like x squared plus 3x plus 2. And it's like, no, they're not. They're nothing alike. But they are alike if x equals 10. If x equals 10, they're actually the exact same thing because 10 squared plus 3 times 10 plus 2 is exactly 132. So they're exactly the same if x equals 10. Now, for polynomials, though, where the domain is all real numbers, many times x does not equal 10. So that's how they would be different. They're alike because if x equals 10, they're the exact same thing, but they're different because x can be anything for polynomials. Okay, so number two, they want you to write something similar to this using this type of notation. So the 5 would be here, the tens, the hundreds, and this would be the thousands. Now this one's a little different too because the leading coefficient is not 1, it's 2. So you would have a 2x squared plus 6 multiplier, 2x cubed because if it's a thousand spot, 6x squared plus 7x plus 5. And when x equals 10, they would be the same. Okay, so they're telling you how you add, and they want to know how you could compare these two to polynomials. And all they want you to do is change this to a polynomial and this to a polynomial and this to a polynomial. And what you would get is x squared plus 3x plus 2. And you would get 4x squared plus 5x plus 1. And then if you would add those up, you would get a 3 here. You have 8x here. And you have 5x squared here because we add like terms. And that would be the same thing as 583. So the math makes sense when x equals 10 on these polynomials, and that can help you understand why you just add like terms. So how does adding polynomials compare? Well, if x equals 10, they're very, very similar. As long as the polynomial doesn't have something like this, negative 9x squared, because leading coefficients can be negative, and that won't be anything like whole numbers. Or what if you had a 13x squared? What do you do with the 10 spot? You would have to move it over to the thousand spot. So it really only works if the leading coefficient is between 1 and 9, really. But it's kind of a nice little comparison. Okay, this is why I cut your assignment short because these are pretty tedious to work on. And I do want you to spend some time thinking about it. I'm going to talk to you about E, which is m of x adding to n of x. So this is the first time we're going to take a line and we're going to add it to a what is that? Quadratic. I was going to try to make that graph paper bigger. Let's see if I can. I needed to scroll down first. Okay. I'm sorry, I should have had this together. But I want you to be able to see it. Paste. Okay. All right, so we're going to take m of x, and we're going to add to it n of x. So what I did is I redrew both of them on here. You could try to juggle it up by looking at one and then the other. But especially now that I have different color ink, I'm going to go ahead and put both of them on the same piece of graph paper. So here's my grid. Okay, I'm going to take m of x, which is negative x plus 1. Negative x plus 1. We'll graph that here in blue, since I already have blue. I make all these dots, and then I get disappointed when my line doesn't touch them all. Oh. Okay, good enough. It's a little wobbly, but pretend. And then I got to graph this other guy. Pink. N of x, which is this x squared minus 2. It's a regular parabola over 1 up 1, over 2 up 4. Over 3 up 9. Okay. So like we talked about yesterday, we know what the sum will be by combining like terms. It's going to be x squared minus x minus 1. Now, that's a lot harder on F, which I want you to try on your own. On F, I did not do it by hand because it would take you some time. I just did it with the graph. But this is the one I want to talk to you about. So if you go, I always start at 0 personally. Let's do green as our answer. Green is going to be our answer. If I take this spot on the m of x, which is your line, and I take 1 plus negative 2, 1 plus negative 2 is negative 1. I'm going to be here at negative 1. Okay, now go over to the 1 spot, and I have a 0 plus a negative 1, and I get negative 1 again. Okay, go to the 2 line, and I have 2 plus negative 1. 2 from this graph. Oh, I kind of did in the wrong order there. Negative 1 and 2, but it doesn't matter with addition. So that would put me here at the 1. And on the 3 line, I have 7 and negative 2, which is 5. Okay, and the negative 1, I have 2 and negative 1, which is 1, which makes sense. And I'm seeing the symmetry now. And in this negative 2 line, I have 2 and 3, which is 5. Once again, the symmetry. And my last one would go off the chart here because it would be the 7 and 4, which is 11 off my chart. So that means that the vertex would be here, and it's hard for me to see exactly where the vertex would be by my graph. What the answer book did here, it actually changed your scale to go by 2 so you could see it better. You guys know, though, if I would complete this square, it would be a negative 0.5. It would be an x minus 0.5 squared, which would put a 0.25 in the corner, and I would be going down 1 1/4. So that's why it's in between there. It is a parabola. When you add a line to a parabola, you're still going to get a parabola. This one will be a little interesting too. It's a cubic. I want you to try that one on your own, but I wanted you to see me to do this one. So the green graph is my answer, and it is kind of a smushed in there. It's a little bit narrower looking, even though it is not squeezed at all. It looks narrower because it looks like but if I would go over 1, up 1, it's still in between, and over 2, up 4, it's still in between. It is not squeezed at all. It's just the lattice points are not where we're used to them being. Okay, ask me if you have any questions there. Again, I shortened the assignment. It took a little bit longer than I thought.